Hello everyone, my name is Nico. Today we are going to talk about social network analysis in Python. So all the course content of this notebook can be accessed following this address. This will open an online Jupyter newbie viewer for this notebook, as you can see. So Network X is the most popular network package in Python. You can use it to create analysis uh, graph object in Python environment. So you can install NetworkX by pip install NetworkX. Uh, and for an Conda user, you can install using Conda install NetworkX. So make sure your NetworkX is version 2.2 or above. So for pip user to upgrade to this version, you can use pip install upgrade NetworkX. So first, let's import NetworkX into the environment. And so suppose we are going to creating a graph, suppose like this. So in this graph, each node represents people, and the different color of edges represent their different relationship. This relationship can be their family, their friend, their coworker, or their neighbors. Um, and the edge weight represent the number of times coworkers had lunch together in a year. So by running this time g.nx graph, you can create an undirected graph object in Python. Then you can add edges from above graph into this empty graph. So this will add an edge between node A and node B. Their weight is 6 times, and their relationship are their family. So by running this, you create a graph to mimic the above graph. Then you can check the graph you create by plotting it. So using this line will help you plot the graph object G in this notebook. So it will be look like this. You can also create a graph object from adjacency list. So suppose here we have a list object where each element represents an edge between node A and B. They are assembled in tuple format. So using NX from edge list method, you can create a graph using this list. So here you can see a parameter called creating using. This will tell the NetworkX to create a graph object based on what kind of graph. So here we are creating an undirected graph like this. So suppose we're changing this object to DI graph, then it becomes a directed graph where in this list there's an edge from A pointing to B. You can see from A pointing to B. We have also adjacency matrix. So suppose we have a data frame like this to represent relationship between each node. So in this graph, there is an edge from C to E, but not from E to C. So we are supposed to create using directed graph engine. So here using nx from NumPy matrix, then put this data frame in, then creating using directed graph. Then you can create a graph object in NetworkX. So if we try to draw this directly, you can find the node name is not the node name is not assembled into this graph object. So we are supposed to rename the node. So it will create from this using creating the node name from this matrix using column index and row index. So here we first create a node name dict from 0 to 8 to the real node name. So it will be like the map each like a column index into a real node name. Then using nx dot relabel nodes, then put the graph in and the name dict to the graph object. Then it will automatically rename all the node. So this is a graph object creating from the above adjacency matrix. You can write the current graph into a GML file by nx.writeGraph g, then followed by the GML file name. It will create so it will create a test.gml file in current folder. Then you can also like reload the current GML local like GML file directly into the Python environment by using nx.read GML, then followed by the file name. It will create the exactly the same graph. So then let's talk about how to add or change node edge attribute in NetworkX. First, let's check what this G is. So in Python, everything can be seen as an object in so this graph G is a directed graph object in NetworkX. Let's store in this address in your local memory. You can access all the graph nodes and edges with their associated information by print out g.node data equals to true, and g.edges. This will access node information, and this will access edges information. You can see here, basically network has stored each node and the edges as tuple, where node A, B, C, D were encoded in tuple format, and there is a dict store their associated information. Hence, we can add, remove, change their information by directly access the node and edge, then manipulate it based on dictionary manipulation. So let's try it. So suppose we are trying to make node A to D to be green node, then node E to H to be blue. So this is a for loop to access each node in A, B, C, D. So this time will then node G I will be node A. First access node A, then node B, then node C, then node D. So for this each node, let's change its color into green and follow the same step. Let's try to change the EFGH node to be blue node by running this line. You can see before there is no node relationship, node information in a previous graph, but here we have changed their color. We have added a color attribute into each node, then change the A to D to be green here, and change node E to H to be blue here. So follow the same steps. We can also change each edge's weight into any random weight here by running this cell. You can see the edge weights had changed. So let's plot the graph again. First, let's try to extract the node color and the edge weight by this. This is a list comprehension style, writing style in Python. So this will it is act like exactly like the for loop here, but more concisely. So for C in node G, extract its color attribute into node color. Then for each edge in node edges, extract its weight into edge weight. Then let's plot Jolly's network again. This time we will encode the node color into the node color we just extract. Then node weight as edge weight we just extract. So running this, we can see there is very light edges where their weight are very small, and each node was encoded in the color we just ensembled. Okay, let's talk about graph visualization. Suppose we're trying to visualize US states relationship based on their movement of their population, which calculate as weight attribute in the following data frame. So first, let's load this data frame. You can see the first two columns are states, and here is weight, which represent their population movements. And we are creating a graph based on the above data frame. As you can see, the graph is very ugly by using the default layout. So as we're trying to enhance the visualization here, we can do a couple of things. First, we can locate each state by their physical location. That's longitude and latitude. Then we can use node size to represent their population. Then we can also emphasize the edges that have larger weight. So let's first read related information. Here we have another data frame which each state's population, their longitude and altitude are encoded in it. Then let's first change it into a dict. Then for add, so we are going to add related information into the previous graph we just created. So for node in g.nodes, this will iterate each node in the graph, in above graph. Then we change its attribute. We added two attributes, that's population and position, where population is the population here, then position is a tuple. In example, it's longitude and altitude into it. So by running this, we can check. So we can see for each node there are two more attributes added into the graph. That's population and position here. Then we first extract its position, then adjust its node size by its population in this node. Then we also extract its edge width, which is its weight object in above graph by running this, and then plot this one. As you can see, the graph is much more beautiful than before. We can also analyze graph using NetworkX, for example, the previous graph. So let's first create this graph again. So there are 10 nodes. Suppose, let's first check this. Suppose we're trying to find who is connected with person C. We can access person C's neighbor by directly using g.neighbors, then put C in. This will return C's neighbor in above graph. And also we try to know who is the most important person to see among above 3 people. So we can rank their neighbors based on their co-launch time. So first we extract its neighbor, then we extract each neighbor's weight with person C, then store that into Panda series object, then rename the series index, then sort values of them. Then we can see among the above 3 neighbors, people E have have the highest co-launch time with person C. So how should person J to get connected to meet with person G? We can answer this question by asking what's the shortest path in the above graph. So we can directly access the shortest path by using nx.shortest path. Then put G in, then followed by the 2 nodes J and G. Then this will give you the shortest path from J pointing to G. So we can ask who is the most important person in the above graph. So, well, to that question, we can have multiple answers. Suppose we try to measure that based on who know more people. That will be the node's degree. So we can directly using g.degree, then put that into pandas series and sort values again. This will give you the rank of people based on their number of neighbors. That's degree distribution. We can also try to measure that based on who have the shortest path towards the other people in the network. That will be the closeness centrality. So from closeness centrality basically measures centrality in a network, which calculated as the reciprocal of sum of lengths of the shortest path between the node and all the other nodes in the graph. So the more central a node is, the closer it is to other nodes. We can directly access that using nx.closeness centrality. Then rank it. So this will give you their each node's closeness centrality. You can see based on this ranking, both people E and people C are very important in the above network. Also, we can try to measure that based on who serves as the bridge to connect the most people in the graph. That will be the betweenness centrality here. So betweenness centrality basically count number of times a node acted as a bridge along the shortest path between every two other nodes. So we can access that by index dot betweenness centrality here. You can see also people E is the most important, but C is very closely ranked as second important person. Also, suppose we want to know how many coworker cluster in the network. We should first filter edges that are not coworker relations, then generate a connected component based on subgraph. So let's create a edge filter based on their relation is not coworker, or each node's relation is coworker. Then creating a subgraph based on this filter, then access a connected component of this subgraph. This will give you, so based on pure coworker relationship, there are two clusters in the above graph. That's C and F. They eat together a lot, then followed by D, E, H, I, J. So you can access more analyzed algorithm using this address. We can also using network X to generate and compare a graph object. So graph theory can be traced back to the 18th century, where mathematicians proposed to use graph as a framework to analyze the Kelsey-Berger bridge problem. So this problem basically is whether there are any way to walk over all the bridges once and only once and return to the same place. So after that, many famous graph models were proposed to mimic real-world problem. So we can consider a graph as a new framework or methodology to solve real-world problem. Among these famous graphs, there are basically four categories of network models. They are regular lattice, where in this graph model, basically each node will have exactly the same number of neighbors. This structure usually can be found in many man-made structures, for example, a neural network model. So the second one will be random graph model, that's ER graph, which are generated by starting with a set of disconnected nodes, then paired with a uniform probability. The third category will be small world networks. So this graph is generated by creating a regular graph, then rewire each nodes with a certain probability. So this network can mimic most real-world human networks relationship, and this network usually have relatively high modularity compared with the above graph, and about the same shortest path between every two nodes that randomly picked. Also, there are scale-free network, that's SF graph. So these networks uh, this network whose degree will degree distribution will follow power law distribution. Um, that's why they are called scale-free network. So this network usually used to represent network relationship in internet. For example, number of friends uh, in social media like Instagram or Facebook. We can generate and compare different network structure. So we first generate above 4 graph in graph 1 to 4. Then let's plot it. As you can see, the above 4 graphs are very different from each other. So there are many network property we can compare, but here we are going to use heterogeneity as an example. So we can measure heterogeneity in a graph based on their degree distribution. So let's try to measure that using Gini coefficient. You can follow the link to check what Gini coefficient is. Basically, it is a very widely used metrics to measure the skewness of distribution. So the higher Gini coefficient is the distribution is more skewed and there are more imbalance in each node here. So here is the formula. We store that each graph's Gini coefficient in a dictionary object. Then by directly get the degree distribution of each graph. Then running this cell, we can find among the 4 graphs, scale-free, the SF network will have the highest Gini coefficient, then followed by the small one network, then is the random graph, then is the lattice, which each node is completely the same. So from above result, we can find this network, this SF and the SW network are like the most the network with the highest heterogeneity. That's each node are very different from each other, where the lattice is completely the same. So how about other network properties? I suggest you to check this very interesting paper. You can follow the link to find this paper. So this paper compare very famous network model based on 3 categories, that's heterogeneity, randomness, and modularity. You can see modularity is the local cluster here. Whether this graph have high local cluster, have many local cluster, then it's graph with higher modularity. And we can see the lattice network is the graph here with absolutely no heterogeneity, no randomness, and no modularity. But the random graph is the one with the highest randomness. And the SF and the SW network are graphs here. Basically, they have higher heterogeneity, relatively randomness, and relatively middle modularity. So in the previous notebook, we talk about how to use Network X to analyze a graph in Python. So in this notebook, we will talk about some graph-based algorithms. The course content can also be accessed using these address. So there are a couple requirements you need to install. It's simple JSON, JSON, and the sklearn package in Python. You can pip or conda install that using uh, this line. Um, so in a previous notebook, we found that graph can be used as a general framework to summarize and analyze real-world problem. So here we are going to introduce some. First, also the most famous one will be the PageRank or TextRank algorithm. So this is the underlying algorithm that controls the search engine, Google search engine result. Then is the graph-based recommendation system. So basically, all recommendation system can be considered uh, uh, as a graph-based algorithm, no matter it is like a people recommendation in LinkedIn or Facebook, or item recommendation in Amazon or Taobao or something. So the basic idea of like modern recommendation system will be collaborative filtering. For example, we build a matrix and the column is different items and the rows is different people. Then basically we trying to figure out whether these people will like this item. He or she did not buy it by looking for the most similar people, or people have the same taste with this person. So this is basically adjacency matrix can be seen as a graph object here. Also, there are probabilistic graph model. This was considered as the most difficult model in modern machine learning. It can be a very basic or very simple based network to predict whether the wet grass was caused by the sprinkler or caused by rain, given the probability of we observe the weather is cloudy, or it can be as complicated as like a graph to analyze your neuron connection in your brain. So I listed a couple very famous paper here. If you are interested about them, you can go forward and looking for this paper. So in this notebook, we will first talk about Google's very famous PageRank algorithm, then explore its replication in NLP area, which is TextRank, for text extraction or text summarization. Then finally, we will generate an industry network based on company's 10K annual report. So let's first check the theory of PageRank following this video.
Given lecture, we are going to talk about a concrete example how to calculate page ranks for a given network of websites or web pages. In this case, we have 4 web pages, A, B, C, and D. As you can see, we are able to model the network with a directed graph. Basically, the connections represent the links. So A is pointing to B. What does it mean? That website A contains a link pointing to B. Okay, C is pointing to B, B is pointing to D, and so on. So what do we have to do? Basically, we just have to use this equation. So the page rank of a given site in the next iteration is the page rank of the given site in the previous iteration, and basically we just have to consider pages that are pointing to that given page, and we have to divide it by the number of outgoing links. Okay, so what about the zero iteration? Basically, this is how we initialize our system. So we just have to define all the nodes or web pages in our network, and basically we are going to initialize the page ranks for every single website to be equals to 1 divided by n, where n is the number of total pages or total websites. 1, 2, 3, 4. So that's why at the beginning all of the web pages will have page rank 1 divided by 4. Okay, of course we have to make several iterations because these values are not the valid page ranks. We just have to initialize these values to be 1 divided by n because we don't know the page ranks by default at the beginning. Okay, what about the first iteration? Okay, so let's consider node A. What are the nodes pointing to node A? Basically, we just have a single node, the node C. So website C is pointing to website A. So we just have to calculate the page rank of this website that's pointing to node A in the previous iteration. What is the page rank of node C in the previous iteration? 1 divided by 4. And we just have to divide it by the number of outgoing links as far as node C is concerned. 1, 2, 3 as you can see. So that's why 1 divided by 4 divided by 3. So the page rank of A in the next iteration is going to be 1 divided by 12. What about B? We have to consider web pages pointing to this given website. So website B. 1 divided by 4 is the page rank of A in the previous iteration. How many outgoing links are there as far as website A is concerned? 1, 2 as you can see. That's why we have to divide it by 2. Plus, we have to consider node C. C has a page rank 1 divided by 4 in the previous iteration, and we have to divide it by the number of outgoing links. How many outgoing links are there for node C? 1 as you can see, 2 and 3. So 1 divided by 4 divided by 3. It has something to do with node A. It has something to do with node C. Okay, so 2.5 divided by 12 is going to be the page rank of website B in the first iteration. What about C? We just have to consider all the websites pointing in the direction of C. Okay, 1 divided by 4 divided by 2. That's all about the node A. And 1 divided by 4 divided by 1. That's all about node D, because node D just have a single outgoing link as you can see. Okay, what about node D? Basically, we have to consider all the websites that are pointing to node D, so node C and node B. What's the page rank of node C in the previous iteration? 1 divided by 4 divided by 3, because C has 3 outgoing links. Plus 1 divided by 4 is the page rank of B in the previous iteration divided by 1, because B has just a single outgoing link. So that's why the overall page rank for website D in the first iteration is going to be 4 divided by 12. As you can see, if we sum up all the page ranks for all the websites in the network, we are going to end up with 1 in all of the iterations. 1 divided by 4 plus 1 divided by 4 plus 1 divided by 4 plus 1 divided by 4 is equals to 1. 1 divided by 12, 2.5 divided by 12, 4.5 divided by 12, 4 divided by 12 is equals to 1 again. So no matter what iteration we are considering, the sum of the page ranks is going to be 1. We just have to consider every single website in the network, and if we sum up the page ranks, we end up with 1. What about the second iteration? Okay, A is 4.5 divided by 12 divided by 3. Why? Because C is pointing to node A. What's the page rank of C in the previous iteration? 4.5 divided by 12 divide by 3 because website C has 3 outgoing. See again, as far as iteration 2 is concerned, the sum of the page ranks is equals to 1. But what does it mean? That basically we are going to have the page ranks. The higher, the better. 4.5 divided by 12 is the greatest number within these values, so we can say that node C is the most important website within this network. Then node D. And as far as I am concerned, it is quite counterintuitive because as you can see, D is not a very important website. Then why is it going to have PageRank value 3? Because a very important website is pointing to that given website. C is a very important website in this given network and it's pointing to node D. So basically it's very important to understand the basic concept behind Google's PageRank. So why is it important to define this equation like this? Because I have created a website 3 months ago and basically no one is interested in this website. Okay, there are several blog articles, for example, in this website, but whenever someone is looking for integer knapsack problem in Java, so let's type it, integer knapsack problem in Java, basically my website is not going to be in the first results. I guess it's going to be in the 10th page or something like this. So what does it mean? That my website is not considered to be an important website by Google. And basically this equation is going to make sure that I am not able to hack Google in the sense that basically I just have to make several web pages. For example, I create 10,000 web pages and those web pages are going to point to this given website, Global Software Support. What does it mean? That lots of websites, lots of nodes are pointing in the direction of this given website, Global Software Support. So we may have the intuition that Global Software Support is very important and basically Global Software Support is going to be in one of the first search results. So basically I just have hacked Google. But it is not going to be feasible because Google's PageRank algorithm doesn't work like that. If we create lots of websites with very low page ranks, basically it doesn't matter that a given website is pointing to several other websites. Basically this is what I would like to show you, that if we have a website without any outgoing links, but a very important website is pointing to that given website, it means that D will have a higher page rank. So we are not able to hack Google. It doesn't matter that we have several low page rank websites pointing to globalsoftwaresupport.com. That website is not going to be more popular, it's not going to have better page rank, hence it's not going to be in one of the first search results when we search for the topics included in the website. We have to make sure that several websites with high page ranks are pointing to a given website. This is when a given website is going to be important, and this is when a website is going to have a higher page rank. So that's all about this little example.
So from the above video, we know the basic idea implemented by a graph-based ranking model is that voting or some kind of recommendation. When one node links to another, it basically casting a vote to that node. So the higher number of votes that are casted to a node, the higher the importance of the directed node. Moreover, the more importance the node casting the vote determines how important the vote itself is. So information can also take into account by so this information can also take into account by this ranking model. The score of the importance of the PageRank score in a graph can be represented as this formula, where D is a damping factor, usually set to 0.85. Then it is like a weighted weighted sum of the the score of all the node that pointing to this node vi. Then the weight is 1 to the number of outgoing links of this neighbor node vj. So let's build an algorithm, build this algorithm in Python from scratch that then apply it to a text network. Well, this method also called text rank, which paper can be found following this link. So let's first load related package. So here we have a text. So in mathematics, graph theory is the study of graphs, which are mathematical structure, blah, blah, blah. So this is a text I just extracted from a Wikipedia page, talk about the graph theory. Then so for the PageRank algorithm, the input is a graph object. So let's first build a network based on the above text. So we will build an undirected text network based on the input string, where edge is the word convention relationship, where we will build an edge between word A and word B if they are convention in a sentence, which this sentence is basically like an equal length sentence based on the above text. So their convention in such sentence is larger than some threshold, arbitrary threshold. Here we set it to 2. So first we replace characters letter note A and Z, A to Z. Then we replace multiple space into 1 using regular expression here. Then we split the above text into words. Then remove stop words and empty object. Then we build an empty subsentence list to store the subsentence. Then for every word in this text, we extract generated subsentence based on the split number, where each subsentence will contain 10 words. So this will extract first 10 words, then followed by the second 10 words, then the next, something like that. So here is a list of an empty list to store the nodes in the text network. Then for each combination of these words, then we if their count, their convention in such subsentence is larger than the threshold, then we append it as nodes here. Then we generate that using this node adjacency list. By running this, we can build a graph, like a text graph based on the above text. Here we can see the graph is the most important words in the above sentence. Then, so let's implement this graph-based ranking. So first we define a class called graph-based ranking. Then it requires several input, which is first is the graph itself. Then is the damping factor. We set it to 0.85. Number of max iterations is the iterations which is the maximum iteration to implement this algorithm. Then it's eta. Eta is the error rate. So if for every round in the iteration, if the node importance score stop, like update, or like their delta value is less than this error rate, then we will break the iteration, then give you the convergent value. Then here is the total nodes in this graph. We store it into the nodes object in this class, number of nodes. Then we're starting by, so this self.score is the PageRank score or importance score in this algorithm, which we will iterate to make it convergence to a certain value. We initialize it to 1 to the number of nodes, 1 to the number of nodes as the algorithm design. So in the fit method, we will starting by creating a for loop to iterate, then store the last score to compute the convergence value of each iteration. And for nodes in each, so for node in each nodes in the above graph, we first extract its neighbors because it is an undirected graph. So we use self.nx.neighbors to extract their neighbors. Then get weighted sum of the nodes neighbor's importance value. So for each neighbor in its neighbors, we extract their neighbor's importance value, then multiply by 1 towards the number of outgoing links of this neighbor, store in temp object, then update the node's score based on this formula. Then for each iteration, we will calculate the convergence value, which is the last score, which is the score in the last iteration minus the score in this iteration, then extract its mean. So if this convergence value is less than some arbitrary error rate, we will break out the iteration. Then there is also a summarize function in this class where we will extract the number of components based on the score we just get from the previous iteration. Then this is sorted all the nodes based on their score, then get the first number of component. Here is the the 5 component with the largest score. So let's test it. Then based on this PageRank algorithm, we can find the most important 10 words in the above graph or in the above text is graph object, graphs, edges, mathematics, vertices, study, discrete, arcs, and mathematical. So you can also access this algorithm easily in NetworkX by calling nx.pagerank. It will give you about the same result or exactly the same result. Also, people have made various improvements to make it more suitable for NLP related work, and PageRank has been also been embedded into Jinsiming, so you can find it follow this link. Let's try it. So from Jinsiming summarization, then import keywords. This is the PageRank in Jinsiming. Then this text is above text. Then just use keywords text, then split. It will give you the Jasmine embedded PageRank algorithm. So we will talk about another very important application in NLP area using graph model, which is called text-based industry network. Well, it is not only can use to build industry network or firm network. It can also be used to analyze customer network, or where you can, which is largely widely used in the digital marketing area, where you separate each customer into subgroups where you customize their need, customize their marketing strategy or campaign idea based on their needs. So let's first try to build a text-based network based on this example. So you can find the original paper following this link. So there are 4 steps to build a text-based industry network. Well, one will be first extract keywords from firm's 10K. Then second will be build a bag of words representation of each document. Then we estimate firm cosine similarity based on the bag of words model. Then apply a threshold and build network. So let's first load related data. As you can see, in this data, so there are 3 columns, and GP key is the company key, then followed by company name. Then here is the 10K report, or here is a document or text to describe the company's business area. So in the sample data, it contains 1,000 firms 10K in 2014. So let's first extract keywords. We can directly use the PageRank or TextRank algorithm we talked in the previous steps. Then, well, because extract 1,000 document is time consuming, we will only showing you how to use it here. Then we will use pre-extract the extracted keywords for this task. Then so we have a set of keywords that related with each document. Then we will build a bag of words representation. So in this bag of words model, basically the columns are different words or words fragment or n-grams. Then each rows are different document, where if this word is mentioned in this document, we tag it with 1. So in this way, you can represent a document by using a word factor. So here is a factor of word. Here is a binary factor that represents keywords in this document. So we can easily build a bag of words representation using counterfactorize in sklearn package, where you can run this cell. Okay, so this returned factor matrix basically is a matrix that have a row number which equals to the number of documents, and the column number which equals to the keywords or the nouns we used to build this bag of word representation. Here we have this factor. We can check the shape of this this matrix by using np.shape. So we can also count how many words or each document or each firm used by running np_sum here to check its distribution. So we can find most of the firms use about 800 to 1,000 keywords here. Then we calculate each firm's cosine similarity. Every pair of firms' cosine similarity. So cosine similarity is basically a widely used measurement of document similarity in NLP area, where it will measure the cosine of the angle between two non-zero factors. Basically, in the above example, this factor matrix, each rows represent a factor which is a binary factor representing keywords mentioned in this document. This will be like every two. So this will be from A, then this will be from B, and this will be the factor we just mentioned or just built using a bag of word model. Then the cosine similarity will measure the cosine of this angle theta. The formula is like this. So we can calculate it directly using cosine similarity in sklearn matrix and pairwise. So by running this, you can calculate the similarity of like every two pair of firms based on their bag of word factor representation. Then we can check the similarity distribution here. Then following fourth step, we can build an industry network based on this similarity network, this similarity matrix, and a threshold. So the basic idea will be, so from the above distribution, we can find if every two firms they have a similarity score larger than 0.6, it will be very likely will be like a pair of rivals or a pair of companies work share the very similar we share a very similar business area. Then we first build a mask or adjust the similarity based on this threshold. So if the similarity matrix value is larger than this threshold, it will be as it is. Then similarity of every two firms, if they are smaller than this threshold, we set it to 0. Then we adjust the diagonal value into 0 in this matrix. Then directly using NX star from NumPy matrix to build an undirected graph based on the previous similarity matrix we just calculated. Then we also adjust or rename the label, relabel the nodes based on their original name. By running this, we can build an industry network. So let's check with a financial company, see what kind of related firm it will have. So we use First Clover Leaf Financial Corp as an example. We first extract the number of these focal companies neighbors, then print it out to print the subgraph out. So we can see basically its related firm are also banks or financial agency and using this firm as a focal company, this sub-network or industry net, its related industry network will be like this. Well, that's all I got for you. So thank you for your attention.